I have this talk kind of split up into three pieces if you look at the outline. The first is just kind of vocabulary. It's so that when we talk about what happens with metals as you put stress on them and as they begin to be in an elastic range, or when they begin to actually really permanently deform, I want to be able to talk about what the vocabulary is, because this is what engineers, throughout the world will use to describe the different behaviors of metals under strain and stress. So, okay, first part is just kind of introductory things for people that build frames. The things that you as a builder are interested in are typically diameter, wall thickness, how straight is a tube. Wall concentricity is probably a thing that most builders don't talk about, but it's something that has a great deal of influence on the reliability of a tube. And that's basically if you had a center line through a tube and then you measured the inside diameter and the change of radius. It's kind of a way of measuring the wall thickness in an odd way. That's how we get our measurements for it. But if what you want is you want that wall thickness to be consistent. Because under stress, anywhere where it's thinner, well, that's where the highest loading force per unit area is going to go to, and you're probably going to have a failure. Or at least it can be. So we tend to look at those things very carefully, certainly more so than most builders do. We actually have hardness testing capability as well. We'll get into that a little later. And then I think the next thing we need to talk about is tensile numbers. And tensile numbers really, if we were to talk about these curves, this is where you start to put a stress on a material. Actually, it's on this axis, and the strain is how much it's dimensionally changing. For instance, if you take something, you pull it apart, and you put a certain amount of force on it, you can actually measure how that cross-sectional area is changing. And that's a measure of, actually it's a measure of, at the crystalline structure, it's a measure of the bond strength of all these little chunks of iron and carbon that are in what is called a body-centered cubic matrix. It looks like CNH sugar cubes. You guys will see that later on. So one of the things that we like to talk about is tensile, and for most of the tubing that's available on the market currently, here, see if anybody else needs a few of those. So one of the things that we like to talk about is about the strength of the commonly available materials. Some of those are, chromoly, and if you're talking about certified aircraft tube that you buy from one of the guys to build aircraft, it starts at about 85,000 KSI, or 85,000 pounds per square inch. The stuff that we sell that's made into butted tubes has some cold work, which is the good side of this part of this that we're going to talk about a little bit later. And those tubes will start at around 110, 115,000, and they can go up or down a little bit. And then from there, you can heat treat those chromoly tubes, and you can get a little bit more strength out of them, and still have acceptable ductility, not that, which is, I'll show you why we don't want that. And then from there, you get into some of the higher strength materials that have their own properties, things like refined grain size that makes them stronger. They have other constituents that glue the grains together a little bit better, and that's how you come up with the so-called air-hardened steels, for instance. Now I kind of want to start talking about this graph and what this is about, because this has really good bicycle applications. When you're riding along on your frame and you're going over kind of a rough road, your frame is actually doing some movement. We've all seen it, in particular in fork blades, they're moving. Well, all of that kind of movement is happening in what is called the elastic range of a metal. And all that really means is that when you have a given force that pushes against it, it bounces back. It's not permanently getting bent out of shape, for lack of a better word. Where we get concerned, of course, is where we get to the limit of what that will come back to. And this is what is referred to as either a proportionate limit or a yield point. It means that the material has plastically deformed. It's stretched and it's not going back. So when we're looking at stress and strain, these are the two. This is strain. This is force per unit area. So what that means is when I pull on this, it gets smaller, but as long as I stay within this elastic range, it will come back like any other spring will. And in fact, that's a really good way of talking about it, is whether you're talking about stress, strain in tensile or in compression, the two are essentially the same, because you're talking really about the bond strength of these things at a microcrystalline level. Let's talk about yield. We did a little bit with that. What engineers do throughout the world is they use a factor here. This is a slope, and the slope of all these lines for steels are the same as M, if you want to call it that. And when this elastic range starts to go to classic, where material starts to fail, you have to have a way of defining what that point is so that everybody can talk and say the material failed. Well, the common number that is used in engineering is 0.2% of the slope of the line. That's when they're saying, well, it's curved over, it's now permanently bent. And that could be a tiny amount. Sometimes it's imperceptible, frankly. So that's a yield. Tensile is normally considered, if you take these things and they stretch and they get a little stronger in here, they cold work. Wherever the highest point is when you see a manufacturer and they quote tensile, they're quoting this number. It's the highest possible number, whether it's brittle and it broke, or it stretched and it got a little stronger, or it was ductile and it stretched a lot, but it did get a little bit stronger. It doesn't matter. They're always going to quote that highest number. That number has some meaning, but without knowing some of these other things, it doesn't tell the whole story.